Okay, so now we're going to take our discussion of the electric field to a practical situation of what's called a uniform electric field. By the end of this video, you should be able to define what a uniform electric field is, understand what a parallel plate capacitor is, and calculate the electric field inside a parallel plate capacitor. So, let's get started. So this figure here shows an important practical situation that we're introducing here that we're going to see again in the next part of Unit 5. What we've got here are two conducting plates called electrodes. They're face-to-face with a narrow gap between them. One electrode has a positive charge, the other has a negative charge. So this arrangement of two electrodes closely spaced and charged equally but oppositely is called a parallel plate capacitor. So what is the electric field between the two plates? To keep things simple, let's focus on the field in the central region, kind of relatively far from the edges. Okay. So here is a blown up view of the area that we're considering. Now at each point, the electric field is the vector sum of the fields from all the positive charges and all the negative charges on the plates. However, the field of a point charge decreases inversely with the square of its distance. So in practice, only the nearby charges contribute to the field. As this figure shows, the horizontal components of the individual fields cancel while the vertical components add to give an electric field vector pointing from the positive plate toward the negative plate, from the positive plate toward the negative plate. And the exact position of the point that we've chosen is not crucial. Moving either to the right or to the left would produce a similar result. So by mapping out the electric field at many points, we find that the field inside a parallel plate capacitor is the same in both magnitude and direction at every point. And this is called a uniform electric field. And as it's shown in this figure here, the uniform electric field is represented with parallel electric field vectors of equal length. Now, a more detailed analysis finds that the electric field inside a parallel plate capacitor is equal to the charge divided by the area times this constant quantity here. Now this constant, which is pronounced epsilon 0 or epsilon naught, is called the permittivity constant. And it's symbolized by this Greek letter epsilon and has a value of 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. So now there's a couple things to note about these uniform electric fields inside a parallel plate capacitor. The field inside the parallel plate capacitor depends on the charge to area ratio, which is often called the charge density. So if the charges are really packed closely, the field is going to be bigger. This analysis requires that the separation of the plates be small compared to their size. So if that's true, the spacing between the plates does not affect that electric field, and that we can see that this spacing does not appear in that equation at all. And now, although these figures show circular electrodes, the shape of the electrodes, they can be circular, they can be square, they can be any other shape. It's not relevant as long as the electrodes are very close together. And also, the charges on the plates are equal and opposite, so the net charge is 0. In the equation here, that's the Q is the magnitude of the charge on each plate. All right, so let's go ahead and take a look at an example. So if you've ever been in a long highway tunnel, you may have wondered what do they do to deal with the soot and dirt and exhaust that all the cars produce. Well, these long highway tunnels have to have these air cleaners to remove all of that from the passing cars and trucks. So one type, which is known as an electrostatic precipitator, air passes between two oppositely charged metal plates. The large electric field between the plates ionizes the dust and soot particles, which then feel a force due to the field. This force causes the charged particles to move toward and stick to one or the other plate, removing them from the air. So a typical unit has dimensions and charges like this here, where we'll have the air and the dust go in one side. They're about 38 centimeters here, 20.6 centimeters here, about 0.9 centimeters apart, and we get a charge of about 540 nanocoulomb per side. Okay, so we want to figure out what is the electric field between the plates. Well, we'll find the field using this equation here, and the direction is from the positive plate to the negative plate. That's the direction that the electric field points in a parallel plate capacitor, from the positive plate to the negative plate, which in our drawing here, that is to the left. So to figure the area of the plates, we convert the centimeters to meters, and we get an area of 0.0783 square meters. So then, to find the electric field between these two plates, we're going to use this equation here and get an electric field of 7.79 times 10 to the 5 newtons per coulomb. And of course, this is asking for the electric field vector, so we would want to also indicate that this is to the direction to the left. Now, this field, a spark will generate an electric field at 10 to the 6 newtons per coulomb. That'll create a spark in the air. If so this field that we just calculated is just a little bit less than that, which makes sense. The field should be large, but large enough to collect the dust and the soot, but not large enough to make a spark jump between the plates. That would likely be bad in a tunnel with a lot of cars and trucks. Okay, so for in the next video, we're going to take electric fields and we're going to look at electric fields in conductors. We'll see you then.